Hello students, it is April 21st, Tuesday. Before I begin the lecture, I just want to point out a few things. First thing, I don't know about you, but I'm really starting to need a haircut. My hair is getting kind of crazy here. Secondly, homework 10 is now available on my math lab along with homework 9, which was assigned last week. Both of those will be due the same day on Tuesday, May 5th, which is your next test. I'll probably give you one more homework next week, which will be your last homework of the semester. Homework 10 that I'm assigning today is based on just today's lecture. So once we finish this, you should be able to successfully complete that homework. On Thursday, it will be a shorter lecture. I'm planning on using the calculator to show you a more technological side to doing what we're going to learn today. So it's going to go a lot faster on Thursday, and then I will give you a lab to do using the calculator technology to solve the problems. So let's go with today's lecture now on hypothesis testing for one sample. And that just means you're going to only have one group of data that you've collected for your study. You're not going to have two groups or more. You're going to have one group, which makes it somewhat easy to do. First, let's review some things here that we learned that are necessary for hypothesis testing. So let's recall our definitions here of the null hypothesis, H0. Remember, it's a statement always with an equal sign. Always, always, always. Also remember that it represents the status quo of your population, meaning what is currently believed to be the truth. And then you have the alternative hypothesis, which is HA or H1, depending on the problem. They both mean the same thing. Remember, that's a strict inequality using those symbols. And also, it is used as an opposite or as a challenge to the null hypothesis. And it helps us to determine in a hypothesis test whether or not we should reject the null hypothesis. Meaning, should we reject or not reject the status quo? Should it be updated or not? Third, we haven't seen this in a little while, confidence intervals. These also tie in with hypothesis testing. So I'm going to bring back that idea of confidence intervals to point out some things. So first, remember that a range of values is a confidence interval. And we always have a certain level of confidence and a certain level of error that goes into constructing those confidence intervals. And the confidence intervals are used to estimate the population parameter, the population value, whatever it is. And remember, we're calling that here the status quo. So it's a range of numbers that might contain the status quo. Also remember, our error level is alpha, so we call that the alpha level. But also remember, it's not only just regular error, it's the probability of type 1 error, meaning the probability that we wrongly reject the null hypothesis. So let's see how confidence intervals and hypothesis testing goes together. So last week I pointed out there's a left tail test, a right tail test, and a two tail test in hypothesis testing. So if you look at a left tail test, remember that HO, your status quo, always goes in the middle. Because in statistics, the middle is really where everything that is significant will occur. Okay? So then HA will go in the left tail. So also remember that with confidence intervals, we're trying to estimate the status quo. So wherever you see HO, that's the actual range of confidence that we're going to put in the problem. And notice here that in this problem here, the confidence level starts at a certain value, and then it keeps going to infinity. And then, of course, the complement of that, remember, is the error, the amount of area that is in the tail of the bell curve. And notice here that the error is our alpha level. Confidence is 1 minus alpha, the complement. If you add these two expressions together, it adds up to 1. The right tail test is just the flip-flop of that. And now the two tail test, this is really what you learned with confidence intervals. We learned confidence intervals start at one number and end at another number. We didn't learn these confidence intervals over here where the confidence interval might go to infinity or it might go to negative infinity. We didn't look at those, but now we will. So here, one other thing I want to point out, remember, is that with a two-sided confidence interval where you have one tail and another tail both shaded in, that's when you take that error and divide it by 2. And notice over here in the one-tail test, the error is not divided by 2 because there's only one tail for each of those. When you have two tails, the error gets divided by 2, and then your confidence is right there in the middle with the null hypothesis. All right, so let's talk about the goal of hypothesis testing and some new terminology. So first, number 1 here, what is the goal of hypothesis testing? It's to decide whether or not to reject the null hypothesis. Secondly, what do we do in order to determine that? So we're going to be looking at steps that we take to make this decision. So what we're going to be using is our observed data, the data that we collect, to compute what's called a statistic. And since that's being used in a hypothesis test, we call that our test statistic. Now, if the statistic is unlikely under the status quo, okay, now if the test statistic is unlikely under the status quo, that means that our test statistic value is much different than the status quo. So in other words, our data will not agree with the status quo. And remember, your data is supposed to be something that's updated, something that's current. Because sometimes the status quo can be a year old, and that might need to change over time, because the numbers will always change, as we know. So what does that mean? So if your data, your test statistic, if that is different than the status quo, if it's different than the null hypothesis, that's what we call statistical significance. All right? So that means that there is a significant difference between what I just found in my research and what is currently believed to be the status quo. Okay? Now, so in other words, our statistic is statistically significant, meaning it is several standard deviations from the value stated in the null hypothesis. And remember, when you're several standard deviations away, that is significant when you're far from the center. And so that means if we're far from the center, we're going to reject what the center is. And that means we're rejecting the status quo, our center. So we don't think that's true anymore. Now, the opposite of this. So number 4 is the opposite. So if the test statistic is likely under the status quo, that means they're about the same. So that means that the statistic is not statistically significant. It's not different than the null. It's not different than the status quo. So we do not reject the status quo. Okay, so now we just talked about the goals of hypothesis testing. So now we're going to talk about what are the steps that we take in hypothesis testing. So these 5 steps is what is called the classical approach. So number 1 we did last week when we talked about the introduction to hypothesis testing. We write out our null and alternative hypotheses using the right symbols and the right numbers, and then we label it as a left-tailed, right-tailed, or two-tailed test. And also remember that at this point, we're initially assuming that the null hypothesis or the status quo, we're assuming that it's true, and then we're going to take our statistics and see if we can still conclude that or not. Now I'm going to show you a picture for number 2 here to illustrate what this means, but we're going to be finding what's called a critical value. And the critical value is just going to break your bell curve into the HA and HO regions, okay? And that's based on your alpha level value, meaning whatever your error is, that error is going to be a certain portion of your graph. And then there's going to be a z-score that will mark that particular position. It's like finding probability. Number 3, we're going to compute our test statistic from our sample data. Number 4, we'll be able to, at that point, decide whether to reject or not reject the null hypothesis. And then number 5, we're going to just make a sensible conclusion in the context of the problem. So let me illustrate a picture here with steps 2 and 3 and 4 to really help you kind of see how that will work. All right, so let's pretend that we're going to set up a left-tailed test as an example. So remember, for a left-tailed test, we need a less than sign for the alternative hypothesis. So our null is always an equal sign, so our parameter equals a particular value. The alternative is that that parameter is less than that particular value. So with a left-tailed test, we shade in the left tail, we label it HA, and the center is HO. And this particular number, whatever that is on this axis, we don't know what it is here, but whatever it is in any problem, that's what your critical value is. And we usually call it Z sub C or T sub C, any letter, whatever it is, sub C, all right, to correspond to our critical value. So now our test statistic. Think of your test statistic now as like a dart. And think of this graph as a dart board. So assuming that when I throw the dart, it's going to hit either the HO portion of the dartboard or the HA portion of the dartboard. Okay? So let's say I have two darts. One of them hits A in the HA region. One of them hits B in the HO region. So what does that mean if your test statistic is where A is? What does that mean? So first it means that you're going to reject HO. Can you see why? Did it hit HO? No, it hit HA. So that means we're going to be supporting HA if your target hits HA. Simple, right? Just think of it as like a dartboard. Wherever the dart lands, that's the one you go with. Okay? So now what about B? B hit the HO region. So that means we will not reject HO. All right? And it's as simple as that once you have the numbers. That's the whole idea. Now, in each problem that we're going to do, you will only have one test statistic. You don't always end up with an A and a B. Okay? You just get one statistic and you see where does it land, HA or HO. Okay? But notice the conclusion here. It's always either you reject HO or no reject. Okay? Now, so if you are using critical values for Z, so like going back to this, that would be Z sub C. So the table that we're looking at here is trying to find this number here for us. And if it's a two-tailed test, it's going to find two numbers for us. So we did some of these already. Like for example, these we found when we did confidence intervals. So if our error here, our alpha is 10%, this actually corresponds to a 90% confidence interval. So these numbers might look a little familiar from last week. However, if you don't have two tails, if you have one tail, these are the numbers that you use. So again, I would just copy this problem or print it out so that you can use it for every problem. Every problem will be asking you for a number from this table that you need. All right, so 2 slides ago, I set up for you the 5 steps of hypothesis testing using what's called the classical approach. There's also a second approach, which is also as popular, so it's a little more popular than the classical approach, is the p-value approach. So the p-value approach is pretty much the same thing as the classical approach with one difference, and that's replacing step 3 of the classical approach. Step 3 was to find a test statistic. So here we're going to be finding the p-value of our test statistic. So you either find the test statistic or you find its p-value. So what is a p-value? It's the probability of any other sample statistic being as extreme as the one that is observed. So the one that is observed is your statistic. And what we're looking for is the probability that any other statistic is more extreme than that. So if you're on the right side, you're going to be looking for the probability of the area being higher than that particular number. If you're on the left side of the graph, extreme would be to the left of the one that you observed. Okay? So now what do you conclude from a p-value test? So if your p-value is less than the alpha of a number, remember alpha is the error. So if your p-value is less than the error value, you're rejecting the null hypothesis. Otherwise, do not reject the null hypothesis. Here's an example to explain why this is. All right, so let's say we have a right-tailed test. And let's also suppose that alpha is 0.05. So what does that mean that alpha is 0.05? That means 5% of the area is in the right tail because this is a right-tailed test example. Now what we're going to do is consider 2 statistics, which we don't know, but we know they're positioned here. Right? So we know that A is in the HA tail, so that means we're rejecting HO. But what does that mean in terms of the p-value? That's what we really want to talk about here. So when you look at A, this is our observed statistic. The definition looks at the probability that any other statistic being as extreme as this one. So as extreme, that means from here and higher. Okay, so to be extreme or more extreme than A, that's going to be from A and higher. So if you were to highlight that, now it's this little green area. All right, so what does that say about A? So first, this area here is a fraction of the blue area that I already highlighted. So if the blue area is 5% and this green area is a fraction of that, then that means its area has to be less than 5%. So therefore, that area is the p-value. Because remember, area is probability. So, and that's what p stands for. It's a probability value. So if the area is less than 5%, the p-value is less than 5%. So therefore, we reject the null hypothesis HO because your p-value is less than the alpha value of 0.05. Now, whereas B, so when you look at B and you find, all right, well, what's the right tail area of B? Because it's a right tail test, so find right tail area. It's more than 5% because this green area is covering more than the blue tail area. All right. Remember the blue tail area was this portion. B covers more than that, so it has to be more than 5% area. So therefore, B's p-value is more than 5%, which would be our conclusion here. Otherwise, do not reject the null. Okay, and finally, before we get to our examples, here are the formulas that we're going to be using for one sample test statistics. So if the problem involves estimating a proportion or little p, then the formula for the test statistic is this. So notice we have p hat. So remember, p hat is your sample statistic. So it's the sample percentage. P0 is the null hypothesis value that is given. So in other words, P0 is your status quo. Also, we have n here. N is our sample size. All right, n would be the sample size. If the problem involves a mean, or mu, then the statistic becomes a t-statistic because with means, we normally have to know standard deviation to compute the statistic. And most of the time, we don't know sigma, but we will know S, which is your sample standard deviation. And remember that if you don't know sigma, then you have to use S as your estimate, and therefore you would follow a t-distribution. If you know sigma, then you would follow a z-distribution, okay? So this would be your formula for the test statistic. So it's x bar, which is your sample average, minus mu0, okay? And here's what those symbols stand for. X bar and S, remember, are sample mean and standard deviation. Mu sub 0 is the null hypothesis value. And of course, n would be our sample size. So now we're going to do a couple of examples involving proportions. So this is from page 490 in your textbook, where it asks you to solve this using both A, the classical approach, and B, the p-value approach. Be sure to verify the requirements of the test. That you can skip. There's requirements, there's other assumptions that we have to check, but we're skipping those. They're really not important for us. They're important for statisticians, but not really for students. So number 8 gives you the null hypothesis that p is 0.6. And then the alternative is p is less than 0.6. Sample size, x is the portion of the sample that has a certain characteristic, and our error level is 1%. So what can we do here? First, let's figure out what our p hat is. So p hat is 124 out of 250. That's what these two numbers mean. So 250 is the total, and 124 is the number of people in this study that have a certain characteristic. So in other words, 0.496 or 49.6% is that portion of the 250. All right, our hypotheses are already given. So what I'm doing here now is I'm writing out the 5 steps of hypothesis testing. So the first step is to list the hypotheses. These are given. But what's not given is that it's a left-tailed test. You can, remember, get that from this expression here. It's a less than sign, so we're looking at the left portion of our graph. Alpha is given as 0.01. Use the table that I gave you a few slides ago to get this critical number. And then that sets up our bell curve on the negative side at negative 2.33. So remember, this is HA. The rest of this will support HO. Our test statistic formula, which I gave you, remember this is a proportion problem, so we're using the first formula that I gave you. Plugging in the numbers looks like this. All right, and as an exercise, try this on the calculator and see if you can get negative 3.36. All right, so right there on my calculator, you can see how I set that up. You're only looking at this part here, this ants minus 1. Don't worry about that. We don't need that. All right, so that's how you would type it in on your calculator if you do it the old-fashioned way. Maybe some of you know a better, cleaner way to do that, but this is how you would enter in that formula to get negative 3.36, round it up a little bit, okay? All right, so now what about this negative 3.36? Well, it falls to the left of negative 2.33. So remember the whole dart and target idea? The dart landed in the HA area. So that means I'm rejecting HO. Okay, so that's my conclusion there, is that the null hypothesis gets rejected in this experiment. Now notice I wrote A here, because right there, that's the classical approach right there, is using your test statistic. So now if we do the p-value approach, okay, it's kind of like an extra step to the classical approach, actually. You do need your test statistic. So remember, the p-value approach is to find the probability that some other statistic is at least as extreme as the one that you have already. So the one I have already is negative 3.36. So when I say as extreme, remember on the left side, that would be more to the left. So I just need to find this left-tailed area of my statistic, negative 3.36. So remember, you can do that using, because this is z-scores, we would use normal CDF. So remember, you have negative infinity, negative 3.36, 0 and 1 are the mean and standard deviation of z-scores, and then it gives you 0.0004. It's almost 0, and it's less than our alpha value. So remember, what that means is when your p-value is less than alpha, you also reject the null hypothesis, since p is less than alpha. Now, what's the difference in conclusions for classical approach and p-value approach? There is no difference. Your conclusion should be the same no matter what approach you take. Okay, so if the classical approach says reject the null hypothesis, then the p-value approach will also come up with the same conclusion. Okay? Now finally, step 5 here, make a sensible conclusion. You really can't in this problem because we don't know what the problem is about. There's no context. So in this problem, don't worry about a step 5. Now, here's a problem with context. So this problem would require a step 5. Let me clear my calculator here. So let's see what we have here. According to the National Highway and Traffic Safety Administration, the proportion of fatal traffic accidents in the United States in which the driver had a positive blood alcohol concentration is 0.36. Suppose a random sample of 105 traffic fatalities in the state of Hawaii results in 51 that involved a positive blood alcohol concentration. Does this sample evidence suggest that Hawaii has a higher proportion of traffic fatalities involving a positive blood alcohol concentration than the United States at the alpha equals 0.05 level of significance? Okay, so the one key word here is proportion. So I know I'm looking at p, not mu. All right. All right, so secondly, I can extract some numbers from this lovely paragraph. So the status quo number is that 0.36. All right, so this is what's already believed to be true. And then from my sample, 51 of the 105 had this particular blood alcohol concentration, all right, or a positive concentration, which was 0.486. Yikes, that's really high. And of course, n is 105. So because this is from a sample, that's our p-hat. The status quo, which is something that's already believed to be true or something that's already been decided or published, is your p0, your null p-value or proportion value. So that right there becomes your null hypothesis. That's what is believed to be true, so we say that's what it equals. Next, so we're looking to see if Hawaii has a higher proportion. So what we're testing is that our null value for Hawaii is higher than 0.36. So that's a right-tailed test, and at alpha equals 0.05, from the table that I gave you a few slides ago, the critical z value is 1.645. And I put it on the right side because it's a right-tailed test, and it's a positive z-score. And remember that this shaded area represents our HA, and this is our null hypothesis in the non-shaded region. All right, so same idea with the test statistic. Remember, it's p hat minus p null. So it's 0.486 minus 0.36, not the other way around. So when you do that, you get 2.690, which is in the tail, because it's higher than 1.645. So since my statistic is more than my critical value, it ends up in the tail or in HA, which means I reject the null hypothesis. So what does that mean? What's our sensible conclusion here? If we're rejecting HO, that means this is no good. So that means I would go with what HA is trying to say, that the proportion is more than 0.36. So in other words, all right, to answer this question here, we can say, yes, there is sufficient evidence that Hawaii's traffic fatality rate is higher, all right, is higher or greater than the 0.36 US rate. Okay? Now, even though I don't have it written on the slides here, let's compute the p-value for this problem. So remember, you do second vars, number 2, normal CDF, and here, so the lower value would be our statistic, 2.690. The upper bound would be 1 E99 for infinity, and then 0 and 1 for the mean and standard deviation. So you can see here that the p-value is 0.0036, which is less than our alpha value of 0.05, which means we would still reject the null hypothesis because this p-value is less than the alpha value. All right, this is number 26, people who talk to their animals on the telephone. How many of you do that? So in an American Animal Hospital Association survey, 37% of respondents stated that they talk to their pets on the telephone. So whenever something is given like that, that is status quo right there. All right, that's what's believed to be true. So now a veterinarian found this result hard to believe, so he randomly selected 150 pet owners and discovered that 54 of them spoke to their pet on the telephone. Does the veterinarian have the right to be skeptical? Okay, so in other words, is the status quo true or not? All right, so we're going to use alpha equals 0.05 as our level of significance. So here are some things we can yank out of that paragraph. Our status quo value of 0.37, so p null. Our sample statistic, p hat, is 54 out of 150, is 0.36, with n equals 150. So the null value is our status quo, so that's your null hypothesis. Now, what's the alternative going to be? So the veterinarian found it hard to believe. So what does he believe? Does he think it's less than the status quo? Does he think it's more than the status quo? You can't tell from this. So that means your alternative hypothesis is two-sided. It could be either or. It could be less or it could be more. So that's a two-tailed test in this problem. Using the table that I gave you with 0.05 and two tails, you use plus or minus 1.96 as our critical z-values. Okay? So the two tails represent HA, the middle is HO, and now the test statistic, following the same formula again for proportions, is set up just like this. Okay? So again, check it on your own, do it on the calculator on your own. Here we get negative 0.25, which is just to the left of 0. The dart is hitting HO, which means we do not reject HO. We hit the target for HO, which means we're keeping it, we're supporting it, whatever you want to call it. But in statistics, we say we don't reject it. Okay? When we mean support it, we mean do not reject it. Okay, so that means we are supporting this. We're supporting the status quo, right? And therefore, we're not supporting the skepticism of the veterinarian. So therefore, that the rate, there is sufficient evidence to conclude that the rate could be 37%, which is our status quo, and therefore the veterinarian should not be skeptical. All right, how do we get the p-value for our test statistic? Okay, so the p-value for our statistic, because it's negative, you want to do a left-tailed statistic. So what I would do then is this second vars, number 2, and I'll be looking at the left tail. So negative 1 E99 up to my statistic, which is negative 0.25. And then the mean and the standard deviation, they stay the same. And there's my p-value. It's 0.40, 40%. So here, this p-value is much higher than 5% error, much higher. So that's the same conclusion that we do not reject the null hypothesis. Okay? All right, folks, let's shift to problems that involve means. So examples part 2, hypothesis testing for a sample mean. So let's take a look at this problem here. The ACT is a college entrance exam, and it has determined that a score of 22 on the math portion suggests that a student is ready for college-level math. Okay, so let's skip down here. So let's suppose a random sample of 200 students who completed this core set of courses results in a mean ACT math score of 22.6 with a standard deviation of 3.9. All right, and these are students that have taken Algebra 1, Algebra 2, and Geometry. So do these results suggest that students who complete the core curriculum are ready for college-level math? That is, are they scoring above 22 on the math portion of the ACT? Right? Because better than 22 means you're doing well. If you get under 22, you're not meeting the standard. So we're concerned about those that are scoring higher to see if they're college-level ready. So here are the numbers we can extract. So first, the 22, that is the status quo. All right, so 22 or higher, right, is really the status quo, but we'll use 22 as our baseline. All right, and these were just given here, right? The mean and sample standard deviation right here in the middle, and n is 200, right? 200 students. So again, the status quo is already given, so we just make that our null hypothesis. And of course, we're trying to determine if that is true or not with an alternative of 22 or higher. So that's this last sentence really here, above 22 would be our alternative. It's a right-tailed test. Okay. And here. So now we don't know the we don't know the population standard deviation, right? We don't know sigma, so that means we have to use t-scores to run this problem. We have alpha is given as 0.05. The degrees of freedom, therefore, would be 200 minus 1, or 199. And so to get our t-score, we're not going to divide alpha by 2, so make a note of this. All right, it's a one-tailed test. We're not using both tails in this problem, so you don't have to divide it by 2, the alpha value that is. Okay, and then you get t sub c equals 1.660. I want to show you the table here real quick because when you try to find the row with 199 degrees of freedom, there isn't one. All right, you get down to 100 and then it skips to 1,000. So since our degrees of freedom is not contained in the table at 199, you take the one that's closest. And 100 would be closest, not 1,000. Okay? So then I'm going to be in this row, and I'm going to need the 0.05 column, which would put me right here at 1.660 as my T sub C. All right? And also note that this is a right-tailed test. This would be a positive 1.660. If this were a left-tailed test, this would be negative 1.660. Okay. So now we put that on the right side at positive 1.660, separating HO and HA on the right. So our test statistic now, because we're looking at a mean score, remember a mean score, we need the formula that finds a test statistic for means. So remember that's x bar minus mu, or mu0, over s divided by the square root of n. So we plug in our numbers, and we get 2.18. So let me show you on the calculator how to do this. Okay, so you can see there on the calculator how I set it up. So you make sure you're using parentheses around the top 2 numbers and parentheses around the bottom 2 numbers to separate your numerator and denominator the old-fashioned way. And you'll get the right answer, 2.18. So note that 2.18 is higher than our critical value. So that means it's going to be in this area here, HA, which means we reject the null hypothesis. So we're rejecting the status quo. Okay? So therefore, all right, what we can conclude here is that the mean could be more than 22 for this particular group of students. And since their mean could be more than 22, that means that these students are college ready for college level mathematics. Because on average, they're scoring higher than that 22 baseline. Now, how do you find the p-value of a t-stat? We've never done that. So I hope at this point you're really watching the video because I'm going to show you something here. So how do you find the p-value for a t-stat for this 2.18? And because it's right-tailed, it's going to be 2.18 to infinity. So you'd have to do second vars. Now we're going to be using number 4. I'm sorry, number 5. I can't read. No, number 6. Sorry, it's number 6. Yeah, I really messed that up. So number 6, we're using, instead of normal CDF, we're using T-CDF. So notice 6 and 2 are very similar, okay? But we use 6 for t-scores. So let's check it out. It works the same exact way. So we want 2.18. We want 1E99 for infinity. And then here it wants the degrees of freedom, which was 199. And we paste it, and there you go. So notice here that our p-value is 0.015, and our alpha value was 0.05. So this value here is less than the alpha value. So that's when you reject the null hypothesis. Since p, this number, is less than alpha, the 0.05. Okay? So alpha is 0.05. One thing I want to point out about this problem, 0.05 is not in this paragraph. It's the next line down, which I didn't copy and paste. Okay? But that was given in the textbook. Okay, so let's do one more problem, and then we're done here, folks. Number 23, calcium in rainwater. So if you're a science person, you might like this. So calcium is essential to tree growth. In 1990, the concentration of calcium in precipitation in Chautauqua, New York, was 0.11 milligrams per liter. And a random sample of 10 precipitation dates in 2014 results in these values. So does the sample have evidence, or does sample evidence suggest that calcium concentrations have changed since 1990? Use alpha equals 0.05. Okay, so what do we have here? First, in this little paragraph, the 0.11 is the status quo from 1990, right? So that's a long time ago, 30 years, right? So that's 0.11. That's what's believed to be true. So now we're going to use the sample data here to determine if that has changed since 1990. Is it the same in 2014? So now, I'm not going to do it on the calculator for you, but you should know now how to type in these 10 numbers into a list, run one var stats, and get the sample mean x bar and the sample standard deviation s. And here you can see that there are 10 values. So try that on your own. Make sure you can get these values. I've rounded them a little bit, except for x bar. X bar, I just took all the decimals. Now also note, no sigma is given, which means we have to use t. So our status quo is the null hypothesis, so mu null equals 0.11. And we want to know if the concentrations have changed since 1990. So changed means, has it decreased? We don't know. Has it increased? We don't know. Could it be both? Yeah, it could be one way or the other, right? So it's a two-tailed test in that case. So when it's a two-tailed test, remember you have to do alpha divided by 2 to divide the error into both tails. All right, so now alpha is 0.05 divided by 2 is 0.025. The degrees of freedom are 9. So now using your T table, all right, the 9th row and the 0.025 column, you'll find T is 2.262. That's our critical value, which sets up the graph. All right, and because it's two-tailed, you put the 2.262 on the left as negative and positive on the right. The test statistic, next step. Using the formula, we plug in the numbers that we know here. All right, we got those from the calculator, and then you get 1.70 for the test stat. which ends up being in the middle portion here, which is going to not reject the null hypothesis because the dart is hitting the null hypothesis target. Okay? All right, so now what does that mean? We do not reject the status quo. So now to answer the question, have the calcium concentrations changed since 1990? No, right? We're supporting the status quo from 1990. So that means calcium concentrations could have remained the same since 1990. You could also say calcium concentrations may not have changed since 1990. All right, finally, what's the p-value for this? What is the p-value for this? So what I'm going to do is I'm going to just copy and paste my code from the previous step because it's the same ID here, right? Because my test statistic is on the positive side, I'm going to be looking at from that statistic to the right. So we're going to use the right tail for a positive statistic, all right? Now, if this were negative 1.70, we would be using negative infinity, okay? But here it's on the positive side, so it's going to go from 1.70 to infinity. So this is already set up. I got to change my degrees of freedom to 9. All right, so delete, delete. All right, and there you go. Now this p-value is slightly more than our alpha value of 0.05. So 0.06 is more than 0.05. So therefore, we still conclude not to reject the null hypothesis. Again, because the p-value is more than the alpha value of 0.05. Okay, and that is the end of our lecture. So again, you can complete homework 10 now that is available on my math lab. And this Thursday, we're going to do problems like these again, but we're going to do it a much shorter way using technology. And then you'll have a lab to do based on that. So you all have a wonderful day and take care. Bye.